Okay, let's wait until 32 and we'll get started. All right. So welcome everyone to the Analytical Sociology Seminar. Today we are very pleased to receive Geoffrey Wodtke. Geoffrey is an associate professor of sociology at the University of Chicago, and he graduated from the University of Michigan. During the past 10 years, he has made significant contributions to the literatures of neighborhood effects, income inequalities, racial attitudes, as well as methodological contributions by developing research methods for causal inference with observational data. He has published in numerous prestigious journals, such as the American Sociological Review, the American Journal of Sociology, or Demography. And today, Geoffrey is presenting a paper on the joint impact of neighborhood poverty and environmental-led contamination on child development. So we are very excited to have you here, Geoffrey, and the floor is yours.
All right, thank you so much for having me and for that very kind introduction. Let me just make sure. Can you guys see my slides okay? Yes. All right. So try and there we go. So this talk is based on a co-authored study with Sagi Ramaj, who's a doctoral student at University of Toronto, and then Jared Schachner, who's a postdoc at the Mansueto Institute for Urban Innovation here at UChicago. And this study is part of a larger project kind of investigating whether the effects of neighborhood poverty on children might be explained by differences in exposure to environmental health hazards, kind of broadly defined. Today, I'm going to focus narrowly on one particular hazard and an American case that is probably somewhat unique, but I think that the broader theoretical model connecting poverty to child development through environmental health inequalities is more widely relevant and will hopefully hold the interest of an international audience. So what's the motivation for this study? First, there are relatively few studies of neighborhood effects during infancy and early childhood. Even though this is the developmental period when socioeconomic disparities in cognitive development kind of first emerge and then become entrenched. Instead, research on neighborhood effects has mainly focused on school-age children and adolescents. Second, there are also few studies of neighborhood effects at any developmental stage that investigate the causal mechanisms that are thought to explain them. And a frequent kind of criticism of research in this area is that neighborhood effects are like a black box or that they arise from like magic dirt. And this is a real problem because analyses of these sort of mediating processes are important both for testing and refining theories of neighborhood effects, but also for developing policies to mitigate them. So in this study, I'm going to investigate first whether growing up in a disadvantaged neighborhood, specifically during early childhood, affects cognitive ability measured at around the time of school entry. And then second, if it seems that neighborhood poverty does matter during this early developmental period, you know, what might explain these effects? So most theories of neighborhood effects highlight mechanisms such as differences in school quality or socialization by peers and resident adults that are really primarily relevant for older children. So instead, I'm going to consider whether differences in exposure to environmental health hazards and neurotoxic lead in particular, whether these might play an important explanatory role early during the course of child development. So some of the most basic features of the neighborhood surrounding children, include the air that they breathe, the water they drink, the buildings they live in, the outdoor spaces that they play in. And in many poor and also racially segregated neighborhoods, the air, water, buildings, soil are contaminated by chemicals that often pose risks for a variety of cognitive impairments, especially when exposure occurs during infancy or the toddler years. So this pattern of environmental inequality is a function of several different and interrelated processes, including the siting of toxic infrastructure, unequal investment in housing, disparate regulatory enforcement, and residential sorting. So for well over a century now, governments and businesses have confronted a dilemma of where to place necessary but noxious infrastructure like factories, highways, landfills, partly by pursuing what's sometimes called the path of least political resistance. And this has often involved selecting sites in or near communities with many poor and minority residents because they're just not as well equipped as their more affluent or influential counterparts to mount effective political opposition. Unequal patterns of housing investment also lead to environmental inequalities. So an ongoing flow of capital into the local housing stock is important for reducing exposures to environmental hazards, since older dilapidated or abandoned structures are more likely to expose residents to some of the harmful materials that may have been used in their construction. Historically, in the US, the practice of redlining and the use of covenant agreements function to restrict housing investment in low-income, Black and also immigrant neighborhoods. Today, market forces and zoning restrictions kind of interact with more subtle prejudices to produce similar outcomes. And so after, the construction of toxic infrastructure and housing divestment expose residents to health risks, ongoing regulation and abatement of these hazards is necessary, but it's also costly. And in an era of kind of chronically strained government budgets and increasingly powerful business interests, disadvantaged neighborhoods tend to suffer from weaker enforcement of environmental health regulations. And finally, all of these factors kind of shape an ongoing process of residential sorting that just reproduces and perpetuates these inequalities. So as some neighborhoods become sites of noxious infrastructure, dilapidated housing, unabated, unregulated toxins, families that are able will pay to avoid them. And this just tightens the connection between neighborhood composition and environmental hazards and exposes many residents to many residents of disadvantaged neighborhoods to harmful chemicals. And so in the US, one such chemical is lead. It's a neurotoxic heavy metal to which children in poor, racially segregated neighborhoods are disproportionately exposed because many different sources of lead contamination are more prevalent in disadvantaged communities. So household contamination by lead-based paint is the primary source of exposure among contemporary cohorts of American children. So during the first half of the 20th century, lead-based paint was a very popular wall covering in homes, and it was widely used in interior construction until the 1970s. And over time, lead paint peels, it chips, it disintegrates into dust. These chips and dust settle on floors and windowsills. Kids get it on their hands and they ingest it. And lead paint was banned for use in residential construction in 1978, but it's still routinely found in older homes located mainly in poorer neighborhoods throughout the country. An important secondary source of lead exposure arises from lead plumbing. So lead came into widespread use in water distribution systems as early as the 19th century. Lead pipes and lead solder were widely used in household plumbing, as well as in the service lines that connect homes to city water mains. And when lead plumbing corrodes, it can contaminate drinking water, which is then ingested by residents. And so the use of lead in potable water systems was also prohibited in 1986. But over 6 million lead service lines remain in use across the US, and older buildings in poorer communities still frequently contain lead plumbing, mainly lead solder on copper pipes. So a third source of lead exposure involves airborne emissions and relatedly soil contamination. Excuse me. So the combustion of leaded gasoline emitted massive amounts of lead into the air until the 1970s, when restrictions were first imposed on its use. Today, the majority of airborne lead emissions come from industrial facilities that process materials containing lead, like smelters and battery manufacturers. But the contemporary legacy of leaded gasoline and, a once very robust metal processing industry in the US is lead contamination of the soil. So airborne lead eventually settles to the ground, where it can remain indefinitely because lead doesn't biodegrade. And as with interior sources of lead contamination, soil lead levels also tend to be much higher in neighborhoods with lower income levels because of their proximity to polluting industry and highly trafficked roads. So many disadvantaged neighborhoods are contaminated by lead, and this is a risk factor for a variety of cognitive impairments among children. So any resident of a lead contaminated environment may encounter the toxin, but infants and young children are by far the most susceptible to all of the exposure pathways that I just outlined. So children drink more water and breathe more air per unit of body weight than adults. They more often play on floors and engage in frequent hand-to-mouth behavior, making them more likely to ingest leaded dust or lead chips. And after lead is ingested, children's bodies absorb it more easily and efficiently than adults. And then within the central nervous system, lead inhibits the proper absorption and binding of calcium and zinc ions, which disrupts many different biological processes. High dose exposure causes acute symptomatic poisoning, which is extremely serious. It can lead to coma or even death. But but acute symptomatic poisoning is pretty rare among recent cohorts of American children who are typically exposed to lead at much lower doses. But even low dose exposure is associated with subclinical toxicity in children, and there is no blood lead level that's presently known not to pose any risk of adverse neurological effects during early childhood. And there are numerous studies showing that blood lead concentration is inversely related to measures of so-called general intelligence among children, even at low levels less than 5 micrograms per deciliter. Children with higher blood lead concentrations also tend to perform significantly worse on school assessments of academic achievement once they enter school. And beyond tests of intelligence and achievement, lead exposure has been linked with indicators of impulsivity, conduct and attention disorders, and delayed acquisition of psychomotor skills. So just to kind of summarize my theoretical model here that I've laid out in words, this figure displays kind of an abridged causal graph relating residents in a disadvantaged neighborhood, lead contamination and child cognitive development throughout the first years of life. And so in this figure, A sub t denotes the socioeconomic composition of a child's neighborhood at time t. M sub t denotes a measure of the degree to which a child's neighborhood is contaminated by lead. And Y denotes a child's cognitive ability at the time of school entry. There are also a set of baseline characteristics here denoted by C, which would include things like a child's race and gender, as well as a set of time varying covariates, which would include things like family income, parental marital status. These are denoted by L sub t. And then finally, there are two sets of unobserved factors here, U and V. So I'll just point out a couple features of this model. First, it shows that neighborhood poverty is hypothesized to affect end of study cognitive ability through environmental lead contamination, as indicated here by the paths that emanate from A sub t and then traverse M sub t. It also depicts kind of two thorny methodological challenges associated with estimating neighborhood effects on child development. So first, it shows that there may be unobserved confounding variables here, U and V, right, that affect cognitive ability and that also affect selection into neighborhoods of different socioeconomic composition or with different levels of lead contamination. And because it's very difficult to identify and measure all of these unobserved, all of these factors that affect these selection processes, bias due to unobserved confounding is sort of a ubiquitous threat to causal inference in observational studies of neighborhood effects. And then the figure also shows here that observed time varying covariates, so L here, confound the effects of future contextual exposures and through the paths emanating from A and M into L, right, are also affected by prior contextual exposures. And this just reflects the fact that families select into different neighborhoods dynamically, where past residential choices may affect the time varying determinants of future residential choices. And in this situation, sort of conventional methods of covariate adjustment may be biased, even when all of these time varying covariates, which are known as exposure induced confounders, can be observed and controlled. So these two challenges, unobserved and exposure-induced confounding kind of inform my whole analytic strategy in this study, which I'll turn to now. So look at the joint effects of neighborhood composition and lead contamination, I combined data from the Project on Human Development in Chicago Neighborhoods, or the PHDCN, with data from the Chicago Department of Public Health's blood lead surveillance system. So the PHDCN is a longitudinal survey that began in 1994 with a representative sample of children living in Chicago. Data on sampled children and their families were collected with three different surveys fielded between, the first wave was fielded between 1994 and 97, wave 2, 97 to 99, and then wave 3, 99 to 2002. And my analytic sample here includes a birth cohort of about 1,200 children who were under 1 year of age at the baseline survey wave. So data on lead contamination come from the city health department's blood lead surveillance database. So since 1994, the state of Illinois has mandated blood lead screening for children who live in an area defined as high risk for lead poisoning. And this includes the entire city of Chicago. So children are tested following a recommended schedule at 12, 24, and then 36 months of age, with additional screening until age 6, if indicated by the test results that they've had from 12 to 36 months. Laboratories report all of these results to the health department, where they're compiled into the surveillance database, and in total, the system covers the results of more than 2 million tests and roughly 90% of children born and raised in Chicago through their 6th birthday. So it's near population data on blood lead levels for children born and raised in Chicago. So the exposure of interest in this study, A sub T, represents the socioeconomic composition of a child's neighborhood, which in the PHDCN is defined as a group of 1 to 3 census tracts. So this measure comes from a principal component analysis of several different tract characteristics, including the poverty rate, unemployment rate, the proportion of female-headed households, the proportion of non-white residents, and it's scaled so that higher values represent neighborhoods with a more disadvantaged population. The mediator of interest here, M sub T, represents the proportion of children under 6 years of age in each neighborhood with a blood lead level greater than or equal to 5 micrograms per deciliter. So the prevalence of elevated blood lead levels in a neighborhood provides kind of an ecological proxy for the degree to which a local community is contaminated by lead from all sources. And then the outcome here, Y, is a child's receptive vocabulary skills measured using scores on the Peabody Picture Vocabulary Test, or PPVT. So the Peabody was administered at the 3rd wave of the PHDCN when most sample members were between age 4 and 5, or just around the time that they're starting kindergarten. So I also measure and adjust for a set of covariates at baseline, here denoted by C, in an effort to control for confounding. So these include gender, race, age, the age and education level of a child's primary caregiver, home ownership status. And then I additionally adjust for a set of time varying confounders measured at each wave of the PHDCN. So these include household income, parental marital status, whether a child's primary caregiver is employed, receives public assistance, or speaks mainly English at home. So what am I trying to estimate from these data? So first, I'm just interested in the average total effect, or ATE, of growing up in a disadvantaged neighborhood, which is defined here using potential outcomes notation. So this expression just represents the expected difference in test scores if children were exposed to the sequence of neighborhood conditions given by A underbar rather than some other sequence given by A prime underbar throughout childhood. And so with a many valued exposure, like my index of neighborhood disadvantage, there are essentially infinitely many contrasts between different exposure sequences. So I model the average total effects using a simple linear function where AVG of A underbar just denotes the average exposure over time, and then beta captures the effective interest.
I think, sorry, Adele has a question.
Yeah, if you have questions, just unmute yourself and blurt them out. It's hard to keep track while I'm speaking.
Thank you. No, thank you, Jeff. Sorry about that. So just a clarification question about the, if you go back, I think to the graphical, maybe the definition of the measures. So I was a little unsure about the U's and the V's. So you have obviously the unobserved, but could you give us, and they are unobserved by definition, but are there any particular ones that we should be worried about? Because often, you know, this literature, any literature, is sort of just assuming that they're unobserved, but it's unclear what those things are, like basically are ghosts. Yeah. But we, you know, it's like, what should we be worried about in terms of U and V?
Yeah, I mean, I think there's several. So one might be, you know, economists might, you know, use the term parental skill, which is sort of an amorphous concept, difficult to measure. I think kind of more practical confounders kind of linked with parental skill would be like whether or not a child's primary caregiver or parents abuse drugs, whether they engage in corporal punishment, or the child experiences physical abuse. There's, you know, kind of potentially confounding, you know, like the link between exposure to lead and outcomes might be like the availability of public health or medical infrastructure in a neighborhood. So if sort of elevated blood lead levels are detected early by, you know, a physician or a public health establishment, sometimes that can, you know, trigger a process that results in the remediation of the lead. So I would think about it as the most likely candidates would be, you know, indicators of parental skill, and then sort of access or availability of health infrastructure.
Okay, thank you. Thank you.
Yep. So in addition to the ATE, I'm also interested in the controlled direct effect, or CDE. So the CDE is the expected difference in test scores if children experience different sequences of neighborhood conditions. So here A versus A prime underbar, but the same sequence of exposures to lead contamination here given by M underbar. So this captures an effect of neighborhood disadvantage on vocabulary skills that's not due to some mechanism involving lead contamination. And as before, I model this effect using a simple linear function where gamma captures the direct effect of neighborhood composition from birth through the end of follow-up. And then I also consider the controlled mediator effect, or CME. This is just the expected difference in test scores if children experience different sequences of exposure to lead-contaminated environments, but the same sequence of exposures to neighborhood disadvantage, which is again modeled using a linear function of the average exposure over time. And then finally, I examined the difference between the total and the direct effects, which can be interpreted as a measure of the degree to which lead contamination explains the effect of neighborhood disadvantage on test scores. And this captures an effect of neighborhood poverty operating through some mechanism involving lead contamination. So the ATE, CDE, and CME can be collectively identified under an assumption known as sequential ignorability, which substantively means that there must not be any unobserved confounders for the effects of both neighborhood composition and lead contamination at each wave of the study. So these are strong assumptions, and my approach to dealing with them, which I'll talk more about in a few minutes, is first to conduct a formal sensitivity analysis, which sort of evaluates, the degree to which my inferences or key conclusions hinge on these assumptions being satisfied exactly, or if they're violated to some degree, would we still reach similar conclusions? And then second, I also conduct a falsification test where basically I conduct a parallel analysis on older cohorts of children, right? Following specifically the 6, 9, and 12-year-old cohorts in the PHDCN, following them forward in time, right? And so these groups of children, while not completely insensitive to lead, are much less sensitive to lead exposure at the levels typically encountered in homes and neighborhoods in Chicago than are infants and toddlers. And so if I were to see big effects of lead, a lot of sort of mediation of neighborhood effects by lead among these older cohorts who are biologically much less sensitive, I would interpret that as evidence of confounding, right? And an indication that my inferences targeting the birth cohort would be maybe invalid. But if there is in fact no unobserved confounding, then all of these effects can be estimated by the method of regression with residuals, or RWR. So briefly, RWR is implemented in 2 steps. In the first step, the confounders at each time point are just regressed on all prior variables and then residualized. In the second step, to estimate the contextual effects of interest, the outcome is regressed on the relevant exposures in these residualized confounders. And by residualizing the observed confounders with respect to the past, RWR avoids the problems that arise with sort of conventional methods of covariate adjustment when any of these variables are exposure-induced confounders. So a little bit more specifically, RWR estimates of the ATE come from the linear regression shown here, where L-perp just denotes a residual transformation of the time-varying covariates, and M-perp similarly denotes a residual transformation of the mediator. So these residual terms are estimated from a set of first-stage regressions for the conditional means of L sub t and M sub t given the observed past. And if all these regressions are correctly specified and exposure to neighborhood disadvantage is sequentially ignorable, then RWR estimates of beta in this model are consistent for the ATE.
Jeff, a quick question
And
there.
similarly, yeah.
So that when we do the when we residualize here, so basically we're taking away it in linear term, right? So we're not doing interactions, because you can think about there being interactions, and then you need to do the residualization over that sort of interactive model. Or am I thinking about this correctly?
No, right. So what we need, right, is for this. Let's see if I can. Can you guys see my pointer or no?
Not yet. No, now we can see it. Yeah, now it's working.
Yeah, so we need this model here for this conditional mean of L sub t given the past, and for M sub t given the past to be correctly specified, right? So if there are nonlinearities, interactions, right, we need those in this model, right? And I didn't put down the models that I actually fit here, but the models that I did fit, I assume that this function is basically linear and additive in the covariates.
Right? Yeah.
I also experimented with more flexible specifications, but yeah, you're right that there may very well be interactions, nonlinearities in these models here. And then also in our outcome model here, which you can see I've assumed away as well, right?
Right.
But I'll talk a bit more about sort of robustness to alternative specifications.
Yeah, great. Thank you.
Yeah. So yeah, this is how we estimate the ATE, and then the control, direct, and mediator effects come from a similar regression shown here, which differs from the model discussed previously only in that it now includes the average of M underbar as a predictor, which is computed from untransformed rather than residualized values of the mediator. So again, under the assumptions of correct model specification and sequential ignorability, both for A and M, right, RWR estimates of gamma and theta here would be consistent for the CDE and the CME respectively. So now let's first have a look just at some descriptive results, kind of illustrating the degree of environmental inequality in Chicago. So this figure shows the spatial distribution of concentrated disadvantage and elevated blood lead levels across Chicago census tracts in 1997, when the PHDCN was wrapping up its first wave of data collection. So darker shades of gray here denote greater disadvantage in the left-hand panel, or a higher prevalence of elevated blood lead levels in the right-hand panel. And so several patterns are pretty striking in this figure. So first, in a truly alarming number of Chicago neighborhoods, a majority of resident children had elevated blood lead levels in 1997. So you can see these grayscale variations on the right-hand panel here, basically deciles of the citywide distribution. And you can see that like the median, right, is an elevated blood lead prevalence of around 0.5, right? So those are very high elevated blood lead prevalence levels. Second, which is partly why the entire city of Chicago was deemed a high-risk area by the state when it launched the Illinois lead program. So second, disadvantaged and lead contaminated neighborhoods are very clearly spatially concentrated on Chicago's south and west sides, which are highly segregated, predominantly Black, and suffer from high rates of poverty and unemployment. And even though neighborhood composition and lead contamination are tightly coupled in the city, disadvantaged neighborhoods with relative lower levels of lead contamination and advantaged neighborhoods with relatively higher levels of lead contamination do both exist in non-trivial numbers. So these patterns are also evident in the figure here, which is just a scatter plot of elevated blood lead prevalence rates against levels of neighborhood disadvantage for Chicago tracts in 1997. And as before, this figure is just showing that these measures are highly correlated, but despite this close relationship, there's still considerable variation in lead contamination among both more and less disadvantaged neighborhoods. So this figure shows an estimate for the overall effect of neighborhood disadvantage on vocabulary skills. So specifically, this is the estimated ATE of sustained residence throughout early childhood in a more disadvantaged neighborhood at the 75th percentile of the citywide exposure distribution, rather than a less disadvantaged neighborhood at the 25th percentile. And this is an effect on PPVT scores measured around the time of school entry, so between age 4 and 5. So this estimate is substantively large. It indicates that living in a disadvantaged neighborhood throughout early childhood reduces receptive vocabulary ability by about 1/3 of a standard deviation. So here are estimates of the controlled, direct, and mediator effects. So like the total effect discussed previously, the estimated CDE here compares sustained exposure to neighborhoods at the 75th versus 25th percentiles of the citywide distribution of concentrated disadvantage. And it indicates that growing up in a more versus less disadvantaged neighborhood would really hardly reduce vocabulary skills at all if children were exposed to the same levels of lead contamination. So the point estimate here is close to 0, and doesn't approach kind of conventional thresholds for statistical significance. Here, a failure to reject the null hypothesis of a 0 CDE just means that we can't rule out the possibility that neighborhood effects during early childhood may operate exclusively through lead contamination, but this effect is pretty imprecisely estimated. So I wouldn't interpret this as lead explains everything. By contrast, the estimated CME is pretty large. It indicates that exposure to neighborhoods with higher versus lower levels of lead contamination, so specifically those with an elevated blood lead prevalence of 65 rather than 30%, which roughly corresponds with the upper and lower quartiles of the citywide distribution. This would reduce vocabulary skills by about 2/5 of a standard deviation, even if children were exposed to neighborhoods of similar socioeconomic composition. And then finally, here's an estimate of the difference between the total and controlled direct effect, which we can interpret as a measure of the degree to which environmental lead contamination may explain the effect of neighborhood disadvantage on vocabulary ability. And the estimated difference between these effects is also large in practical terms. if we do a little bit of mental math and divide this difference by the estimated ATE, again, it suggests that nearly all of the total effect is explained by some causal mechanism involving lead contamination. But, you know, again, this difference and the estimated CDE are both relatively imprecise, and so these results are also consistent with only partial mediation.
Can you explain again what's the difference between the CME and the ATE minus CDE? Because to me it's like the same thing. So basically, how lead contamination explains neighborhood disadvantage or differences in cognitive development. How is that different?
So are you saying, sorry, did you say the CME or the CDE?
No, ME.
Yeah, so the CME, right, is basically the effect of sustained exposure to a lead contaminated environment versus an environment that doesn't have as much lead in it. If children were to live in environments with the same socioeconomic composition, right? So it's sort of similar to the total effect of lead exposure, except it's not, strictly speaking, it's not exactly that, because it is represents a joint intervention on both lead and the neighborhood environment. It's like if we were to put kids in the same in neighborhoods with the same socioeconomic composition, but then different levels of lead contamination, right? What would their test scores look like around the time of school entry, right? And then the CDE is similar to that effect, except it's asking if we were to put kids in neighborhoods with the same level of lead contamination, but different composition, right? What would their test scores be at the time of school entry, right? Does that help to clarify?
Yeah, one last thing. It was about the last measure. So the difference between CME and the last measure, ATE minus CDE. Or you explained that already?
Yeah, so so this difference in the models that I'm showing you here, again, I'll talk about relaxing some of the functional form restrictions in these models in a little bit, but in the models that I've shown you here, you can think about this ATE minus CDE as essentially an indirect effect, right? It's like the component of the total effect that operates through differences in exposure to lead. More generally, for example, in models where you know, the effects of lead or the neighborhood environment may be nonlinear or may interact, right? Then the interpretation of this difference isn't really an indirect effect, but you can still interpret it as the degree to which the total effect operates through some mechanism involving lead. Now, that mechanism could be a mediation mechanism. It could also be an interaction mechanism, right? Which is why the indirect effect interpretation doesn't really hold once you relax some of the modeling assumptions here. But it's basically just a way of evaluating, right, whether or not the difference between the total effect and the CDE actually differs from zero, right, as opposed to just kind of eyeing up these different point estimates and drawing that inference.
All right, thanks.
Yep. So so all of these estimates only have a causal interpretation under some strong assumptions about unobserved confounding, And so it's important to kind of get a handle on their robustness to possible violations of these assumptions. So to address this, I implemented a formal sensitivity analysis where confounding bias is modeled using a selection function that captures departures from the ignorability assumptions that we talked about before. So to briefly kind of illustrate what's going on with this sensitivity analysis, it's helpful to just first kind of simplify things and consider an analysis of a point in time neighborhood exposure A. So in this setting, bias and estimates of a point in time ATE would occur if the observed mean outcome isn't exchangeable with the counterfactual mean outcome. And the form and magnitude of this bias we could model with the selection function shown at the bottom of the slide here, where tau is an unknown sensitivity parameter. If tau were less than 0, for example, then estimates of the ATE would be biased downward because children in more disadvantaged neighborhoods differ from those in less disadvantaged neighborhoods on unobserved factors that also suppress their vocabulary skills. Similarly, non-random selection into 2 point-in-time exposures, A and M, right, could be modeled with another selection function depicted here. So under this model, bias and point-in-time variance of the control, direct, and mediator effects is governed by the sensitivity parameters phi and psi. And as before, negative values here would imply that families select into neighborhoods that are more disadvantaged and or suffer from greater lead contamination on the basis of factors that also suppress their vocabulary skills. And then bias corrected estimates of these effects could be computed by using the selection function to construct a bias term, and then essentially by subtracting this bias term from point estimates of the ATE, CME, and CDE. And so basically, I just generalize this approach for exposures that are time varying. So in this setting, I use separate selection functions to model unobserved confounding at each time point, and then modify the bias term so that it reflects accumulated selection from baseline through the end of follow-up. And then to try and make this interpretable, I calibrate the sensitivity parameters so that a unit change corresponds with the amount of bias eliminated from the effect estimates I just showed you by virtue of adjusting for parental education. Right? And so then we can interpret the results of the sensitivity analysis or the bias corrected estimates in terms of their sensitivity to kind of multiples of observed confounding due to non-random selection on parental education. So these figures just plot bias adjusted estimates of the ATE, CDE, and CME as functions of the parameters tau, phi, and psi, respectively. And they indicate that our inferences about both the total and the joint effects of interest are pretty robust to unobserved confounding. So even in the scenario where unobserved confounding is assumed to be twice as strong as that due to parental education, bias corrected estimates for the total and controlled mediator effects are still negative, are still large in practical terms, and we still reject the zero null, while estimates for the controlled direct effect remain small and statistically insignificant. So given that parental education is among the most powerful determinants of neighborhood selection and child vocabulary skills, this level of confounding by unobserved factors seems pretty extreme, but of course, we still can't rule that level of unobserved confounding out completely empirically. So I also conducted a number of other robustness checks. So I first experimented with many alternative RWR specifications, so including some that permit the effects of interest to interact, to be nonlinear, to vary across race, gender, family income. And all of these models yielded similar estimates for the population average effects that I showed you previously. I also computed effect estimates using both inverse probability and entropy balancing weights, which were very similar to those based on RWR, and require a different set of modeling assumptions, arguably weaker. And then finally, I also conducted a falsification test on older cohorts of children in the PHDCN. So again, children older than 6 are, just biologically, developmentally much less sensitive to low dose lead exposures. So if lead concentration appeared to play an important explanatory role among the 6 to 12-year-old cohorts in the PHDCN, this would suggest that sort of the focal mechanism here is confounded by unobserved factors, right? And that my inferences, about the impact of lead during early childhood might be faulty. But in this parallel analysis of older children, I find no evidence of mediation via lead, which I would interpret as a negative falsification test and support for the credibility of inferences specifically targeting the birth cohort. So just to conclude, growing up in a disadvantaged neighborhood appears to substantially reduce vocabulary skills during early childhood, and these effects seem to operate at least in part through a causal mechanism involving lead contamination. And so these findings, I think, have several implications for ecological development theory. So the most influential perspectives sort of linking neighborhood poverty to child development focus on intermediate mechanisms that are most relevant for older children and adolescents, right? So these mechanisms include, differences in school quality, peer subcultures, access to adult role models, collective supervision. So each of these mechanisms, may very well be important for transmitting neighborhood effects on certain outcomes and at certain times, but their influence kind of during the critical early phases of development is really circumscribed by natural limitations on the social interactions of infants and toddlers. And so my results support a theoretical model that views neighborhood effects as kind of first arising from disparities in exposure to environmental health hazards during early childhood. And so these findings also have policy implications. So research on neighborhood effects is often criticized for having limited capacity to inform policy, either because of concerns about the credibility of causal inferences or because this research often reveals little about the intermediate mechanisms that might serve as points of intervention. And so, short of conducting a sequentially randomized field experiment, I think that this analysis provides some of the more credible evidence that neighborhood contexts do causally affect cognitive development during early childhood. And it also identifies a clear mechanism, lead contamination, that partly explains these effects and is also amenable to intervention. And all this suggests that programs to abate lead in homes, replace lead plumbing, remove lead contaminated soil, they'll not only improve child outcomes overall, but they may also help to mitigate place-based disparities in cognitive development. But the study's definitely not without limitations. There are many. I think the biggest ones are that, I've relied on data from a single cohort of children born in a single city, Chicago, nearly 3 decades ago. I've also only considered a single neurotoxin, even though poor neighborhoods are often contaminated by many different chemicals in addition to lead. And the degree to which these different hazards might explain neighborhood effects likely vary widely across time and place. So in some of my current research, I've been trying to address some of these limitations by matching surveillance data on all known or suspected air neurotoxins monitored by the U.S. Environmental Protection Agency to the U.S. Department of Education's early childhood longitudinal studies, which are national in scope and cover more recent cohorts of children. And so kind of early findings from these data indicate that being born into a high poverty neighborhood substantially increases the risk of exposure to many different types of neurotoxic air pollution, and that these differences also play a role in the etiology of neighborhood effects during early childhood. So, despite its limitations, I think this study still provides, pretty strong evidence that growing up in a disadvantaged neighborhood, inhibits cognitive development during early childhood because these environments are literally toxic for children. And as, sociologists kind of begin to illuminate this black box of neighborhood effects, we should probably start to prioritize research on the role of environmental health hazards during early childhood. So that's all from me. Thanks for your attention, and happy to take questions, comments, critiques.
Thank you very much, Geoffrey, for a very interesting talk. We can now